This video is on the two-sample t-test. The purpose of a two-sample t-test, which is also often called an independent samples t-test, is to test whether the means of two populations are equal. For example, let's think about the populations of non-working college students and working college students. Those are two separate populations of people. A researcher might be interested in whether one of these two populations is getting more sleep than the other population. For example, a researcher might be interested in whether working students are more sleep deprived than non-working students. What that researcher is wondering is the mean hours of sleep of the working college student population different from the mean hours of sleep of the non-working college student population? In other words, the researcher is wondering if the average number of hours slept by working college students is different than the average number of hours slept by non-working college students. So if you're doing a study and you want to know if the means of two populations are equal, or if the difference exists between the means of those two populations, then you need to do a two-sample t-test. And when you're using a two-sample t-test, first you have to recruit a sample of participants from each of the two populations being studied and record data from every member of those two samples. So when you're recruiting your participants and you're collecting data, those are the steps of the study that come before the calculations. You only do the calculations after you have your data, and the two-sample t-test is actually the name for the calculations that are done in this type of study. So all of these steps, such as collecting data, such as recruiting participants and collecting data, are leading up to the point at which you do the calculations, and those calculations in this case are called a two-sample t-test. So in my hours of sleep example, the researcher might recruit 100 non-working students and 100 working students. If the researcher is interested in comparing working college students and non-working college students, the researcher has to recruit a sample of working college students and a sample of non-working college students. The researcher has to take a sample of both populations that he or she is interested in. And the researcher collects data from those two samples. So in this case, the researcher would ask the 100 non-working students and the 100 working students how many hours they're sleeping per night. And altogether, the researcher would be collecting the hours of sleep for all 200 people, because there's 200 people total in this study. It doesn't have to be 100 and 100. A researcher might use a different sample size. I just decided to use the number 100. So we're taking a sample of population 1 and a sample of population 2. The null hypothesis in this type of study that uses a two-sample t-test says that the means of the two populations are equal. The null hypothesis says that there's no difference between the means of the two populations. Remember that the null hypothesis is the absence of something. So in this type of study, the null hypothesis is the absence of a difference between the two population means. So in my study, in which I'm interested in whether the average sleep of working college students is different from the average sleep of non-working college students, my null hypothesis says that the mean hours slept per night by working college students is equal to the mean hours slept per night by non-working college students. In other words, my null hypothesis says that there's no difference between those two population means. The null hypothesis says that the two population means are the same number. And let's think about what it means for the means of two populations to be equal. Here we have population 1, which is the working college student population, And here we have population 2, which is the non-working college student population. I looked up how many college students are in the US, and I think it told me that there's roughly 19 million college students in the US. And out of those 19 million college students, there's about 11 million working college students and about 8 million non-working college students. But these aren't exact numbers. These are just numbers that I think are roughly correct. These numbers might have changed since I looked them up online, but let's just pretend that these are the sizes of the two populations. Let's pretend that population 1 has exactly 11 million people and that population 2 has exactly 8 million people. The mean of population 1 would be the total of all 11 million sleep times divided by 11 million. Remember that we're interested in hours of sleep in this study. So what the mean of population 1 would be is the mean hours slept per night by population 1. So to get the mean hours slept per night by population 1, you would need to add all 11 million sleep times, because there's 11 million people and each of those people has his or her own sleep time. And then you would, after adding those 11 million numbers, you would divide the total by 11 million. That would give you the mean of population 1. What about the mean of population 2? If you wanted to actually calculate the mean hours slept per night by this population, you would have to ask all 8 million people in this population how many hours of sleep they're getting per night. You would have to add the 8 million answers and divide the total by 8 million. That would give you the mean hours of sleep for population 2. So overall, to get the mean of population 1, you would ask all 11 million people how much sleep they're getting per night. You would add the 11 million answers, and you would divide by 11 million. To get the mean of population 2, you would ask all 8 million people in population 2 how many hours of sleep they're getting per night. You would add their 8 million answers and divide by 8 million. And you can see how it would be very difficult for a researcher to actually calculate these two population means because, well, first, the researcher would have to actually collect data from all of these billions of people. In order to get the mean of population 1, the researcher would have to collect data from 11 million people. To get the mean of population 2, the researcher would have to collect data from 8 million people. And it's very hard to collect data from that many people. And even if all of this data could be collected, it would be difficult to add that many numbers to get the total. So it would be even if the data could be collected, the calculations would be very difficult to do. So the researcher in this study isn't actually going to calculate the two population means. What the researcher is going to do is take a sample of a certain number of people from population 1 and take a certain number of people from population 2 to be the sample of population 2, and the researcher is going to calculate the mean of sample 1 and the mean of sample 2. So the researcher is going to calculate the two sample means, not the two population means. For example, if the researcher recruited 100 people from population 1 and asked those 100 people, how many hours are you sleeping per night, the researcher would record their 100 answers, add them, and divide by 100, and then that would be the mean of sample 1. If the researcher asked 100 people from population 2, how many hours are you sleeping per night, the researcher would add their 100 answers and divide by 100, and the researcher would get the mean of sample 2. And after the researcher calculates those two sample means, the researcher would use those sample means to be able to make a decision about whether the researcher thinks that the population means are equal. The researcher is going to use the two sample means to make a decision about whether the researcher thinks that the population means are equal or unequal. So the sample means are what are being calculated, but the decision that's being made is about the population means. So the researcher's final goal is to decide whether or not the population means are equal, and the researcher is simply using the two sample means to be able to try to make that decision. And the researcher is typically hoping to try to be able to reject the null hypothesis. In most studies, the researcher is hoping to reject the null hypothesis and support the alternative. So in this type of study, the researcher is probably hoping to reject the null hypothesis, meaning reject the idea that the population means are equal, and conclude that there appears to be a difference between the two population means. The researcher is hoping to reject the null hypothesis and conclude that the alternative appears to be true. And in order for the researcher to be able to make that conclusion, the researcher's data set that the researcher records from the two samples has to support the idea that these two population means are different. So there's three different versions of a two-sample t-test. It can be a left-tailed test, a right-tailed test, and a two-tailed test. The difference between these three types of tests involve the type of critical value that's used and the way that the p-value is calculated. And we'll get into those details a little bit later. First, I'm going to tell you how a researcher decides whether which of these tests to use. If the researcher has a reason to believe that the mean of population 1 is lower than the mean of population 2, the researcher will use something called a left-tailed two-sample t-test. For example, if I'm thinking that the mean of population 1 is lower than the mean of population 2, if I'm thinking that the mean hours slept per night by working college students is lower than the mean hours slept per night by non-working college students, I would use something called the left-tailed test. And in a left-tailed test, the null hypothesis says that the population means are equal, because the null hypothesis always says that the population means are equal in this type of study. But the alternative hypothesis actually goes along with my prediction. I'm predicting that the mean of population 1 is lower than the mean of population 2. That's the claim I'm hoping to support. So that actually becomes my alternative hypothesis in this type of test. If the researcher has a reason to believe that the mean of population 1 is higher than the mean of population 2, the researcher uses something called a right-tailed test. And the null hypothesis still says that the population means are equal, because the null hypothesis always has the equal sign. But the alternative hypothesis actually goes along with what I'm predicting. So if I'm predicting that the mean of population 1 is higher than the mean of population 2, then that becomes my alternative hypothesis. So the researcher is typically hoping to reject the null hypothesis and support the alternative hypothesis. So this is what the researcher is hoping to support in a right-tailed test, this alternative hypothesis. What if the researcher doesn't have a specific prediction ahead of time or a belief about which population has the higher population mean? For example, what if I don't really have any idea about which population should have the higher mean for hours of sleep? But I'm just interested in doing a study to find out which population appears to be getting more sleep. So I'm curious about which population is getting more sleep, but I don't really have any idea ahead of time about which population should be getting more sleep than the other one. In that case, you do something called a two-tailed test, which is when, well, the null hypothesis still says that the population means are equal, but the alternative hypothesis simply says that the two population means are not equal, that they're just different from each other, because in this case, the researcher doesn't have a specific prediction one way or the other, and the researcher is simply hoping to support the possibility that the populations are different in some way. The researcher is hoping to show evidence that the populations are different from each other in some way, but the researcher doesn't have an idea ahead of time about which population mean should be higher than the other one. That's when you use a two-tailed test. So in a two-tailed test, the null says population means are equal. The alternative says population means are not equal. So the null hypothesis always says population means are equal. The alternative hypothesis depends on which version of this test you're doing. In a left-tailed test, the null hypothesis says in a left-tailed test, the alternative hypothesis says that the mean of population 1 is lower than the mean of population 2. In a right-tailed test, the alternative hypothesis says that the mean of population 1 is higher than the mean of population 2. And in a two-tailed test, the alternative hypothesis says that the population means are not equal. And in all three of them, the null says that the population means are equal. So I'll explain a little bit more about what it means to do a left-tailed, right-tailed, or two-tailed test a little bit later on in this video. First, I need to talk about the sample sizes. In a two-sample t-test, your two samples should include at least 30 people each, meaning 30 from population 1 and 30 from population 2. The exception is if you know that the populations are normally distributed, meaning bell-shaped, then you can get away with a smaller sample size. But typically, you don't really know if the populations are bell-shaped, which means you would, to be safe, you should have a sample of 30 people from population 1 and a sample of 30 people from population 2, meaning that should be the minimum sample size you should have. Higher sample sizes would be even better if you can get them. For example, 50 from population 1 and 50 from population 2 would be even better, but 30 is usually the minimum. That's a rough guideline for the minimum. In a two-sample t-test, you calculate something called the T-score. You use the data that you record from your two samples to calculate a T-score. And what the T-score is meant to do is to show how much evidence the data is showing against your null hypothesis, meaning it helps you, the T-score shows how much the data is going against the null hypothesis. So this is the formula for the T-score. It has on the top it's the mean of sample 1 minus the mean of sample 2, the difference between the two sample means. On the bottom we have a square root that has the standard deviations of sample 1 and sample 2 and the sample sizes, the size of sample 1, the size of sample 2, and the standard deviations are actually squared. So This is just a diagram showing that you have these two populations. You're taking a sample of population 1 and a sample of population 2, and you're using the data that you get from sample 1 and the data that you get from sample 2 to calculate the t-score. And the t-score is calculated with the entire data set, meaning the data from sample 1 and the data from sample 2. This is just because of the way the formula works. If the mean of sample 1 is lower than the mean of sample 2, the t-score will be negative. The reason why is because if the mean of sample 1 is lower than the mean of sample 2, and you're subtracting a smaller number by a bigger number, you get a negative number on the top of the fraction. For example, 3 minus 4 would be negative 1. And when the top of the fraction comes out to a negative number, the entire t-score comes out to a negative number. Now, if the mean of sample 1 is higher than the mean of sample 2, then you get a positive number on top when you subtract the two sample means. And then the entire t-score becomes a positive number. So if the mean of sample 1 is 4 and the mean of sample 2 is 3, then 4 minus 3 is 1. It's a positive number. And then the entire t-score becomes positive. If the two sample means are equal, for example, if they're 3 and 3, then the top of the fraction comes out to 0, because whenever you subtract a number by the same number, you get 0. For example, 3 minus 3 would be 0. And when you get 0 on the top of a fraction, the entire answer comes out to 0. So if the two sample means are equal, the t-score will always be 0. Now, it's hard for me to get all of this to fit on the same slide. So maybe I'll scroll over a little bit. What we have here is we have the, well actually, I'll pause, I'll stop this video and start it again.